Oh, yeah.
It's just first principles, right?
Well, first principles uses small angle approximations, but it's not even, you're not even going that far in terms of using first principles. We're simply just using the small angle approximations for sine and cos.
Oh, sorry.
That's all good. So I guess the first question is, do you have like your small angle approximations to hand?
Yeah. Sine theta approximates to theta, and then cos 2 theta to 1 minus a half 2 theta squared.
Yeah, where 2 theta is in the bracket and squared.
And then I got theta over 1 minus theta squared.
Theta over what, sorry?
1 minus theta squared.
1 over 1 minus a half 2 theta squared, right?
Can you not cancel them down?
You can, but I think you might have just cancelled them down incorrectly.
But how? Because it's in front of the bracket.
Yeah, so you have to square first.
And
then halve it.
So theta over 1 minus 2 theta squared.
Wait. That sounds right, yeah. Let's see.
Because it squares to 4 theta.
What's that?
Because it squares to 4 theta squared.
So we have, it's approximately equal to theta over 1 minus a half bracket 2 theta squared, which is equal to theta over 1 minus a half of 4 theta squared, which is equal to theta over 1 minus 2 theta squared. Yep. That is fine. So, is that all good?
Yeah.
Awesome.
What do you do? Is that where you finish?
Pardon?
The question. Is that where the question finishes?
I mean, yeah, pretty much.
Oh, that's the answer.
I mean, that's okay. There is, I mean, technically
you don't sound sure.
What's that?
You don't sound sure.
No, the reason I was saying, technically we can go further with this, and we ought to go further, but we haven't actually done the work to know how to go further with this yet.
Oh, okay.
This can actually be expanded because it says find an expression in terms of theta. This is an expression in terms of theta. I mean, there are theta squared terms as well, but we can actually go further. And there was a different question that we did in lesson as well, where it was something similar, but I didn't let us go there because we still need to do binomial expansion. It's something that we haven't yet done, but that's okay. But just know that we could take this further with binomial expansion. Yeah, but that's okay so far. The main thing I wanted us to do was just to apply the small angle approximations. I've got another question on small angle approximations. Hand play to completion, which is, well, I guess you're just following on the thing.
Yeah, I'm doing both.
Oh, cool.
Is sufficiently small the same as small?
Yeah. So when I say sufficiently small, it's sufficiently small that we can find an approximation, that we can use the small angle approximations. Because small angle approximations don't work for big values of theta because they're quite clearly different. But we can't say that sine of 100 is the same thing as 100 because sine only goes between 1 and -1. So to say that sine of 100 is approximately 100, given that sine theta approximates theta, it's a bit, we can't say that because 100 is way too big.
I'm a bit stuck on sine part. I've done the cos. Because where would the square go?
So sine squared. So remember that sine squared is just sine times sine. So sine of 3 theta times sine of 3 theta.
Aha. I got minus 18 theta to the power of 4.
That sounds reasonable. Let's see. So sine squared theta is 3 theta squared, or 3 theta times 3 theta. And then 1 minus bracket 1 minus a half 2 theta squared. So the 3 theta squared pertains to sine squared 3 theta, and we've got 1 minus, and then the bracket bit is the cos 2 theta substitution.
Wait, wouldn't it be 9 squared theta?
Yeah, it would. 9 theta squared. So I've put 3 theta in a bracket and then squared it.
Oh, okay. Sorry.
That's all good. And then, so I've just done it. That's how I start off. And then I'm going to square it to say 9 theta squared times, well, 1 minus 1 is just nothing. So then I have minus minus. I think you might have forgotten the double minus, because then that becomes plus a half times 2 theta squared, which is equal to 9 theta squared times a half times 4 theta squared, which is equal to 9 theta squared times a half times 4 theta squared is 2 theta squared, which gives you just positive 18 theta to the 4. So I think you did everything just except for that bit where you apply the double negative. I think you might have just put minus. You might have started off with minus a half 4 theta squared and then gone from there and carried that minus the whole way through.
Oh, okay. Wait. Because you know when you substitute cos x is 1 minus a half. And we have 1 already here. So the 1s cancel out, right?
Yep.
And that would leave you with minus a half, no?
Yeah. And so do you see where I've put like the double bracket? So the bracket in the bracket. You would have minus, but remember, it's also all of that is being minused.
Oh.
So you've got the minus.
Oh, yeah.
Yeah.
Brackets.
Yeah, but that's why I always use brackets for things like that. Cool. And then yeah, there's part B.
I was gonna say sub, but there's 2 different. It's pi over 2 and pi over 3.
So yeah, that's one of the issues. It would look like they're different, but what was the original expression?
18 theta to the power of 4.
Well, that was the original approximation, but the actual original expression in the question for part A.
Sine squared 3 theta. Aha!
I like the memorization.
I got 1.3 1.353.
Sounds good. Yeah, let's go through. Yep. So hearing an answer like that, I think that sounds good. Let's go through just the full steps of that. So you realized that 3 theta has been replaced with pi over 2. So 3 theta equals pi over 2. So therefore theta equals pi over 6. For the other expression, we realized that 2 theta was made to be pi over 3. Therefore theta equals pi over 6. So we can unequivocally say that our theta value that we're going to use for substitution is pi over 6. So our approximation is 18 multiplied by pi over 6 to the power of 4. And then that gave you what? 1.354?
1.353.
Yep. It's good to 3dp. And decimals is okay because it is an approximation. I probably would have left it in terms of pi, but actually decimals are fine again because it's just an approximation. So yeah, good stuff. Okay, next slide. Can you differentiate sine of x on first principles? Sorry about that, I'm back.
No worries.
How's it coming along?
Yeah.
Yeah.
Well, managed to differentiate it.
Oh, did you? Nice. So let's just quickly go through it. So we start off with the limit as h tends to 0 of sine of x plus h minus sine of x, all divided by h, which equals the limit as h tends to 0. And then expanding it.
Sine a plus b rule.
Indeed, yeah, the expansion. So sine x cos h plus cos x sine h minus sine x. So the first part was the sine x plus h, and then you still got the minus sine x at the end. And it's all divided by h. And then we can write it like this. Well, I don't know. There are many ways in which you can go about it from here, but I'd probably go like this. Sine x. So the sine x plus h and the minus sine x. Sorry, the sine x cos h and the minus sine x, I probably group them together to say that part is sine x open bracket cos h minus 1. And then I've got the plus cos x sine h all divided by h. And then I can apply small angle approximations on specifically the h's, because h is quite small, it's tending to 0. So sine x open bracket cos h becomes 1 minus h squared over 2, and that's minus 1. And then I've got, pardon me, cos x times h, because the sine h becomes h, all divided by h. And that becomes the limit as h tends to 0 of, so the 1 and the -1 will cancel. And if you have h squared over 2, dividing that by h will give you have your sine of x multiplied by h minus h over 2. And then plus cos x. Because now we can safely divide by the h. And then now that we have no h at the bottom, we can safely apply the limit. Substituting h equals 0, the sine x times minus h over 2 cancels, and you're left with cos x. Nice, 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 nice.